Okay, let us then start today's session. Uh, so, is the screen visible to everybody?
Yes, sir, it is invisible.
And I am clearly audible, right?
Yes, sir.
Okay, thank you. Okay, let's start then. Okay, good evening, everyone. My name is Abhik Deb, and I welcome all of you to the sixth live session of the course Concepts of Thermodynamics, which is being taken by Professors Dr. Suman Chakravarti and Dr. Aditya Bandyopadhyay at IIT Kharagpur. As in for myself, I am a PMRF PhD scholar in the Department of Mechanical Engineering at IISc, and I shall be dealing with the live sessions of this course, wherein we will be solving some of the problems related to the concepts that were discussed in the previous class of the in the previous lecture of the course, so that some of the doubts related to the concepts can be cleared out. Mm, if you have any doubt related to the problems that will be solved in today's session, you can simply interrupt me and ask. Also, since the meeting screen won't be visible to me, if anyone is waiting in the lobby, kindly let me know so that I can let the person in. And I request all of you to be present every Friday from 6 to 7 p.m. to make this program a success. So, without further delay, let us start with the problems. So, problem number one. Today we will be dealing with the energy balance equation for a control volume system, that is a flow system. So, these all of these problems are related to that only. So, let us start now. mm, and the first question is, a 2.5-liter tank, which is initially empty, is to be filled with 10 grams of ammonia coming from a line flowing saturated vapor ammonia 25 degrees Celsius. That is, initially there is a tank which is initially empty. Okay, now from a line which carries ammonia at 25 degrees Celsius, that is saturated vapor ammonia at 25 degrees Celsius, the ammonia is allowed to enter this tank, whose volume is 2.5 liters, and this tank is maintained at 30 degrees Celsius throughout the process. Finally, after a certain pressure is attained, the flow of ammonia is closed, and we have to find out what I mean when this 10 grams of ammonia has already entered into the system, then what is the final pressure inside the tank? Okay, so see, it is given that saturated vapor ammonia fills the tank. For saturated saturated vapor ammonia at 25 degrees Celsius, okay, it is given that initially, what is the volume of the tank? The volume of the tank is, wait, this is not that. Saturated vapor ammonia at 25 degrees Celsius fills the tank. Okay. Now, see, given the volume of tank 2.5 liters. final mass of the tank, sorry, the final final mass of ammonia in the tank. Ammonia in the tank, that is 10 grams, that is 0.01 kg, and this is 2.5 into 10 to the power minus 3 meter cube. Okay, so what is the final specific volume? Final specific volume of ammonia, this is equal to, that is the volume by mass, that is 2.5 into 10 to the power minus 3 divided by, this is actually 10 into 10 to the power minus 3. So this comes out to be equal to 0.25. Okay, 0.25 meter cube per kg. Now, but the tank is maintained at 30 degrees Celsius. Okay, the tank is maintained at 30 degrees Celsius, and the saturated ammonia, it comes at 25 degrees Celsius. So and the tank is maintained at 30 degrees Celsius. So essentially the ammonia inside the tank will be in a superheated state. So from superheated property table of ammonia, property table of ammonia, we can say that the pressure here is the temperature here is given at 30 degrees Celsius and 500 kilopascal. The specific volume is given as 0.2810 meter cube per kg, and same at 30 degrees Celsius and at, so this is constant, and at 600 kPa the specific volume will be 0.2315 meter cube per kg. So we can see that the final specific volume of ammonia at 30 degrees Celsius, when it is maintained at 30 degrees Celsius, is between these two values. So the pressure, final pressure will also lie in between these two values. So we can find the final pressure by interpolation. Therefore, by interpolation, final pressure P2, this is equal to 500 plus 600 minus 500. This is just simple interpolation. 2315 minus 0.2810, and this is 0.25 minus 0.2810. So this value comes out to be 562.62 kPa. Okay. I think so. This is correct only. Yes, this is correct. Okay. So this is the final pressure. So the next question is, in the previous problem we have to find what is the heat transferred to the tank. So considering the surface of the tank, the surface of this tank we are considering as the control volume surface, then the energy equation can be written as dE by dt. This is mi hi plus vi square by 2 plus gzi plus q dot, these are all rates, minus w dot minus Me He plus Ve squared by 2 plus G Z. Okay, so the rate from both the sides we are cancelling, all the dots, and this dt we are cancelling, and dE, that is the change in the internal energy, that can be written as, this is the final mass of the system inside the tank multiplied by the final internal energy minus the initial mass and the initial internal energy. This is equal to Mi, and we neglect the changes in the kinetic and potential energy, that is delta kinetic energy is equal to 0, delta potential energy is equal to 0, and there is no, since it does not involve any moving surface, so the work done will also be 0. Okay, so MIHI minus W, sorry, this is W is already 0, so this will be Q, and minus MEHE. Now in the tank there is no exit, nothing is going out of this system, only inlet from the saturated vapor ammonia line, only ammonia is coming in, but nothing is going out. So the exit mass is also 0. So this value will also be 0. That is, we can say that M2U2 minus M1U1 is equal to MIHI plus Q. Here I am writing Me is equal to 0. Okay. Now again, if we consider the mass balance, then dm by dt, that will be equal to Mi minus Me. This implies that final mass minus initial mass is equal to Mi minus Me. But Me is equal to 0, right? This implies that initial mass, this value is equal to M2 minus M1. Sorry, this will be M1. M2, this will be M1. M1. Therefore, we are putting this, if we put this value in 1, then Q is equal to what? M2U2 minus M1U1 minus MIHI. Okay. Now, M1 is also equal to 0. It shows that, it states that initially it is empty. So, M1 is also equal to 0. M1 is also equal to 0. Initially it is empty. Therefore, Q is equal to M2U2, this is 0, minus Mi. Mi is equal to M2 minus M1. M1 is 0. So, this is again equal to M2 Hi. So, this is equal to M2 U2 minus Hi. Okay. Now, what is U2? Now, what is Hi? Let us first start with the inlet enthalpy. Now, inlet is saturated vapor ammonia at 25 degrees Celsius. So, at T saturation equals to 25 degrees Celsius, the specific enthalpy for ammonia Hi will be this is a saturated vapor state, so this will be enthalpy of the vapor state corresponding to the 25 degrees Celsius. Okay, this is equal to 1460 kilojoule per kg, and at we have already found out the final pressure 562.62 kPa. At 562.62 kPa, and the final temperature is 30 degrees Celsius, the internal energy, specific internal energy, this is U2, this is equal to 1370 kilojoule per kg. Therefore the heat transferred Q, this is equal to m2. What is the mass? Mass, it is given as 10 grams. So 0.01, and you multiply it with 1370 minus 1460. So it comes out to be equal to minus 0.9 kilojoule. This is the heat lost actually. Okay, so this is the answer. So is it clear to everybody?
Hello, sir.
Yes, right.
Yes, it is very clear, sir. It is a unsteady any problem, sir.
Yeah, it is an unsteady problem.
Yeah.
So that is why we are writing the equation for the unsteady, the change in the energy. There is initially in the previous class we were considering that this value is 0. Hence the right hand side we were considering to be 0, and we were solving. In this class, that is why since it is an unsteady process, so the energy is changing, right? Both energy and mass are changing with time. So the equation becomes this. This is the energy equation for a unsteady energy equation for a
Hmm.
control volume process.
Unsteady and filling process. Filling process.
Yeah, it is a flow process.
Uh,
Flow process. It is a control volume process, right? Control volume is one. We consider a fixed volume, but the volume, I mean, the volume can also. We are considering basically a surface whose mass can change and whose volume can also change. So it is basically a control volume system. It is basically a flow process.
okay, sir.
So is it clear?
Yes, sir.
Okay. So then let me move on to the next problem. Okay. So it is a 25-liter tank as shown in the figure that is initially evacuated is connected by a valve. Now this is a tank of 25 liter and it is connected by a valve to a air supply line in which the air is at 20 degrees Celsius at 800 kPa. Now the valve is opened and the air flows into the tank until the pressure reaches 600 kPa. Okay, we are asked that we are told that the process is adiabatic. We have to find what is the final temperature inside the tank. Now you see, from the energy equation we are writing the energy equation. This is the basic energy equation and this is the basic mass balance equation. Now in this case, what is there is no mass that is exiting the system. We are considering this tank to be the control volume. Then only mass is entering. There is no mass leaving the system. Okay, so the mass exiting is 0. Again, initially it is evacuated. It states that it is evacuated. Okay, so since it is evacuated, so the initial mass m1 is also 0 of the tank, and we are neglecting the changes in the potential energy and kinetic energy. So from the balance of mass we can say that the final mass will of the tank will be the mass that is entering into the tank from the air supply line. Okay, now from the energy equation what we will get, this is the energy equation number 1. So with the given considerations we will see that 1 implies m2u2 is equal to mihi plus q minus w. Okay, here the process is adiabatic, q is equal to 0, and w is also 0. See, there is no moving boundary, so the work done is also equal to 0. Okay, so what happens, this equation becomes m2u2 is equal to mi hi. But from the mass balance equation we have found that m2 is equal to mi. Okay, so m2 is equal to mi, then the final internal energy will be equal to the enthalpy of the air that it is entering. Now at 20 degrees Celsius and 800 kPa, that this is the condition of the airline, the enthalpy value is equal to 293.65 kilojoule per kg. Okay, therefore U2 is also equal to this value. Now what we can say we can directly consider the property table value and find out what is the, since u will be a function of temperature only, so from the property table value and corresponding to the final pressure of 600 kPa, corresponding to 600 kPa and U2 is equal to 293.65. This is a function of temperature, right? Final temperature. So corresponding to this pressure and this internal energy, from the property table we can directly find the property table for air. We can find T2 to be equal to 410 Kelvin. Alternatively, what we can also do, at 600 kPa, 600 kPa it is like what, 6 atmosphere, around 6 bar pressure. Okay, so at 600 kPa the value for CV for air, this is nearly equal to 0.718 kilojoule per kg. Okay, sorry, kilojoule per kg Kelvin. Therefore, if we write this value, then U2 is equal to what? CV into T2. This is equal to 293.65. So T2, this will be 293.65, and if we divide it by 0.718, this will essentially come out to be same, 409.6, which is nearly equal to 410 Kelvin. So the final temperature is equal to 410 Kelvin. Okay, now moving to the next part of the problem, problem number 4, we have to find what is the mass of air that has entered the tank. Now the mass of air that has entered the tank is what? This value that has entered the tank, this is equal to the final mass of air inside the tank. So the mass of air that entered the tank mi is equal to m2 minus m1, where m1 is equal to 0 since it is initially evacuated. So this is m2. This is equal to p2 v2 by r t2. So we have found what is the final pressure. Final pressure is 600 kPa. Final volume of the tank is fixed 25 liters. The final temperature we have found at 410 Kelvin. So let us put these values. So 600 kPa multiplied by the final volume is 25 liter, that is 25 into 10 to the power minus 3. R value is 0.287. There is a kilojoule in this, this kilo and this, there is a kilopascal in this, so we are not writing 10 to the power 3 in these cases, so they get cancelled, or we can write it just for better to avoid the confusion. And this is also 10 to the power 3, and what is the final temperature? 410 Kelvin. So this value comes out to be 1275 kg. Okay, so this is the mass of air that has entered the tank. So I hope this is clear to everybody. If it is clear, then we will move on to the next problem.
Sir, hello, sir.
Yeah, please ask.
Sir, in this any problem that HI,
Yeah.
this at 20 degrees centigrade and
Uh,
800 kilopascal,
yes.
this HI value, it is from the air table.
Yeah, from the air table.
Sir, can you calculate this at the enthalpy of the air by using the formula Cp into the temperature?
You can calculate the value, but I mean, this will come out nearly equal to what? Similar value itself. You can see, we can just, right now we can calculate the difference. Right, what is the CP value? CP value is around 1.004 to 1.007. So 1.007, and if we multiply it with what is the temperature value here?
800.
No, that is the pressure. 20 degrees Celsius is the
20
temperature.
degrees, sorry, 20
So
degrees.
20 degrees Celsius is 293 Kelvin. So it comes out, it is 295.
Yeah,
So
yeah.
just a bit difference in the value. So I mean, overall it will be similar. So exactly at 20 degrees Celsius and 800 kPa, the value for CP might not be 1.007. It might be around what, 1.004. So if
Yeah.
it is around 1.004, it comes out 294. So it is almost similar. Okay, so these are, this can be directly calculated. For exact values you can calculate it from the property table, but if you need a almost an average value, then you can directly do it from the, I mean, CPCB values.
Sir, if this question is suppose in an examination,
Okay.
then you will suggest use the property table, calculate by formula.
No, I mean, for the property, if you, in the examination, if you are supposed to calculate it from the property table, then you will be given the property table,
Yeah,
or you
yeah,
will be asked to bring the property table.
yeah.
If not, then you can directly calculate it from there. You can write an assumption
Okay,
that
okay, okay,
I am
okay.
assuming the CP value to be this and CV value to be this, and you can directly calculate.
Okay, okay.
But
Thank
whatever
you.
you were assuming, that has to be written.
Yeah, yeah. Okay, sir.
Okay,
Okay,
so
okay.
it is
Thank you.
clear.
Yeah, okay, sir.
Okay, okay. Then let us move on to the next problem. Okay, so yeah. Now the next question is, a 200 liters tank as shown in the figure below initially contains water at 100 kilopascal and a quality of 1%. Okay. And heat is transferred. Now you can see that this is a state in which it is at 100 kilopascal pressure and at 1% quality, that is the amount of liquid is 0.01. Okay. Sorry, the amount of vapor is 0.01. Okay, now heat is transferred to the water, thereby raising its temperature and pressure. At a pressure of 2 megapascal, this safety valve will open and the saturated vapor, this vapor is lying above, right? So the condition that the vapor that will be going out will be essentially saturated vapor, and the saturated vapor will go out. The process continues, maintaining there will be 2 megapascal pressure inside, and it will be continued until the amount of vapor becomes 0.9 or 90%. Then it stops. We have to find what is the total mass of water that has flowed out. Okay, that has flown out. Okay, now at P saturation, these are all saturation pressures because this is a liquid vapor mixture. So at and x1 is equal to 1%. Okay, if we find out the specific volume of the liquid stage, then it is 0.001043, and the specific volume of the gas state, it is 1.69. Okay, therefore V1 is equal to 1 minus x1 Vf1 plus x1 into Vg1. So this value, if we put in all the values, remember that this is 0.01, this is in percentage. Okay, so it will be 0.01 when we put it in here. So this will come out to be 0.0179 meter cube per kg. Now the given volume of the tank is 200 liters, that is 200 into 10 to the power minus 3 meter cube. Therefore initial mass is what? M1 is V by this specific volume, that is 200 into 10 to the power minus 3 divided by, this is minus 3, and this is 0.0179. So this value comes out to be equal to 11.15 kg. Okay, again in the final state, at P saturation equals to 2 MPa and x2 is equal to 90%, if we write these values 0.001176, these are all the values from the property table. So 0.09967. So V2 will be equal to, if we put in the value 1 minus x2 Vf2 plus x2 into Vg2, we will get this value to be 0.0898 meter cube per kg. Therefore M2 is equal to 200 into 10 to the power minus 3. Since the total volume remains the same, 0.0898, and this value comes out to be 2.2265 kg. Okay, so we have to find out what is the total mass of water that is flowed out. Therefore mass of water that flows out ME, that is equal to M2 minus, sorry, that is equal to M1 minus M2. So that value comes out to be 8.92 kg. Okay, so this is the first part of the problem. Let us move on to the next part. So in the previous problem, we have to find out what is the total heat transfer during the process. Now we from the energy equation, if we write the energy equation here, then see dE by dt, this is equal to mi hi plus vi square by 2 plus gzi plus q dot minus w dot minus me dot he plus ve square by 2 plus gz. Okay, so here what all values are 0. We can see there is no work done. Okay, change in kinetic and potential energy are neglected. Okay, and there is no inlet mass, it is only exiting, so mi is also 0. Therefore this implies M2U2 minus M1U1. Also we are cancelling all the rates from this, from both the sides. Therefore it becomes Q minus, this is ME AG. Okay, but from in the previous problem we have already found out that ME is equal to the difference in the mass. Okay, or let me write it here. Dm by dt is equal to M2 minus M1 is equal to Mi minus Me. Okay, so since Mi is 0, so we can write it as, sorry, dm by dt, it is M2 minus M1, and this is equal to Mi minus Me, and no, this will be the change in the mass. Initially the mass is more and finally the mass is less, and that amount is going out. So wait just a minute. Yeah, wait, so this will be, right, it is M2 minus M1 only. So this is therefore Me from here minus Me is equal to M2 minus M1, and that is Me is equal to M1 minus M2. Okay, in this there is an issue. This will be mass of water that has flown out. Okay, this is fine. M1 minus M2, this is M1 minus M2. So if we put it in the energy equation, what we'll find, therefore M2U2 minus M1U1 is equal to Q minus M1 minus M2 Ag, or you can say that Q is equal to M2U2 minus M1U1 plus M1 minus M2 into Ag. Okay, so this is equal to, so if we put in the values, this will be and U2, U1 and Ag. So we can calculate these values here. Let me calculate the values, U2 and U1. So it will be like this only. At saturation pressure of, at P saturation equals to 100, sorry, P saturation equals to 100 kPa, and X1 equals to 1%, U1, this will be equal to 1 minus 0.01, and from the property table value of the liquid fraction, specific internal energy of the liquid state, if we put in the values, that will be 417.20 plus 0.01 multiplied by 2505.90. so this value comes out to be 438.09. okay, then U2 is what? At P saturation equals to 2 megapascal, and X2 is equal to 90%. So U2 is equal to 1 minus 0.9, and from the property table we'll get it as 905.94 plus 9 multiplied by this value 2597.67. This is the internal energy value of the gas vapor state, and this is the internal energy value of the liquid state. So this comes out to be equal to 2428.49 kilojoule per kg. And what goes out, see, whatever goes out is saturated vapor. So at P saturation equals to 2 megapascal. If we write the saturated, the HE will be equal to enthalpy of the vapor state, saturated vapor state at 2 megapascal. So this value is 2797.03 kilojoule per kg. So if we put in all the values, all these values, 2.23 into 2428.49 minus 11.15 into 438.09 plus this value is 8.92 into 2797.03. So this comes out to be 25480.34 kilojoule per kg. Sorry, not just kilojoule, not kg per kg, because we are already multiplying with mass. So this comes out actually, therefore the heat transferred will be, this is 25.48 megajoule. Okay, so the final heat transfer during the process is this 25.48 megajoule. Okay. So is it clear to everybody?
Yes, sir.
Okay, then we will move on to the next problem. Okay, so the next problem is helium in a steel tank. This is helium. Okay, helium in a steel tank is at 250 kilopascal, 300 Kelvin with a volume of this 0.1 meter cube, and it is used to fill a balloon. Now, when the tank pressure drops to 150 kPa, the flow of helium stops by itself. The helium balloon is still at 300 Kelvin, and we are to assume that the pressure in the balloon varies linearly with the volume. That is, when the pressure inside the volume, when the volume of the when the before the balloon starts to inflate, the pressure is 100 kPa, and finally the pressure is 150 kPa. We have to find what is the final volume of the helium balloon. Now, for this we are considering both the helium, considering now the tank plus balloon as the control volume. Okay, initially what is there is the volume of the balloon is 0, so there it doesn't occupy any space. Only the volume of the tank is the gives the control volume here. So initially the what is the pressure? The pressure inside the tank is 250 kPa, right? And the volume inside, the volume inside the tank is 0.1 meter cube, and the temperature inside the tank is 300 Kelvin. Okay, again, finally what happens? Finally the tank pressure drops to 150 kPa, and the final pressure of the balloon is also 150 kPa. So the final pressure of the system, that is the control volume here, is 150 kPa, and the temperature is continued to be maintained at 300 Kelvin throughout. So the final temperature is also 300 Kelvin. Now see, when we are considering tank and volume, this is the tank. Okay, so this is the tank and this is the balloon. Okay, so when we are considering tank plus balloon as the control volume, what happens? The mass that is leaving the tank is entering the control balloon, but no mass is leaving the control volume. Okay, so initially whatever be the mass in the tank, that mass essentially gets redistributed between the tank and the balloon. So we can say that for this system, the initial mass is equal to the final mass. Okay, so that is Pi Vi by RTI. We are considering helium to be an ideal gas. PF Vf by RTF. But Ti and Tf are equal. Therefore, the final volume Vf is equal to Pi by Pf into Vi. So if we put in the values, this is 250 by 150 into 0.1. So this value comes out to be 0.167 meter cube. But this volume is the volume of the tank plus the balloon. Okay. Therefore, we can write it as volume of the tank plus volume of the balloon finally is equal to 0.167. But the volume of the tank is rigid. I mean, since the tank is rigid, but Vt is equal to 0.1 meter cube. Since the tank is rigid, okay, so there is no change in the volume of the tank since it is rigid. So this will remain same. So only the volume of the balloon is changing. This implies the final volume of the balloon is equal to 0.167 minus 0.1, that is 0.067 meter cube. Okay, so this is the answer. Okay, now the next part of the problem is we have to find what is the total heat transfer to the tank during the process. No.
Sir, hello, sir.
Yeah, tell me.
Sir, please show me the last part of the solution.
Yeah.
I have not noted.
Okay. You have understood this one, right?
Yes, sir.
Hmm.
Sir,
So,
can you again explain this MI equal to the MF?
okay, so see, we are considering the tank plus this balloon as the control volume, right?
Yes,
Okay, so in this control volume, what happens? Initially, there is a particular mass of helium inside the tank, and the
yes,
balloon is there is no volume, that is, there is no mass inside the balloon. Okay, in the final state, what happens? Some mass of helium from the tank moves to the balloon, and the balloon gets inflated, right?
yes,
So
sir.
suppose so this mass, whatever it was initially inside the tank, will now get into the balloon plus the tank finally.
Yes, sir.
But no mass is leaving the control volume.
Okay.
So the initial mass, whatever will be that was initially completely within the tank, will now be within the tank and the control volume
Oh.
throughout. Tank and the balloon throughout.
The main thing is here the tank and balloon is the control volume.
Yeah, tank and
Second
balloon
is
together is a control volume.
a control volume. Yes, sir. Okay.
Okay. So did you understand?
Yes, sir. Just wait, sir. I am writing this.
Okay.
Okay, sir. Now you can proceed.
Okay. Okay. So again, you can see when we are considering the tank and the balloon as a control volume, what happens? There is whatever mass is initially inside the system, the mass finally within the system will also be the same. Okay. So we can write it as for this system, for tank plus balloon as control volume, what happens? m1 is equal to m2 that we have considered. Now we are, I mean, mi is equal to mf. So since we, when we write the energy equation, we have to denote the inlet mass as I, so I am writing it as m1 now. So m1 is equal to m2, that is the initial mass and the final mass are same, and we are making it as m. Okay, and for this system, see, nothing is entering the system and nothing is leaving the system also. If we had considered balloon as the system only, then there would be an inlet mass mi, but since we are considering both the tank and the balloon as the system, there is nothing entering and nothing is leaving the system. So mi is equal to 0 and me is also equal to 0. We also neglect the changes in the kinetic and potential energy. Okay, but before that, see, because of the inflation of the balloon, there will be a work done by this helium gas. So for total heat transfer, we have to find out what is the work done during this process. But it states that the pressure inside the balloon varies linearly with the volume. So if we considered tank and the balloon as a system, see, at V1 is equal to 0.1 meter cube. So what is the initial volume? Initial volume was 0.1 meter cube. In that case, the pressure was 250 kPa. P1 is equal to 250 kPa. And at V2, that is the final volume we have found this is a total volume. We are considering the total volume of the system. So 0.167. Okay, then the final pressure throughout the system is 150 kPa. So pressure throughout the system is 150 kPa. Okay, so what we can write that variation in pressure with volume as P, that will be equal to, initially the pressure is 250, okay, plus the difference 250 minus 150 by the difference in the volume 0.1 minus 0.167. These are just the volume corresponding to these pressures. This is essentially a linear interpolation itself. So, and the volume, the final volume minus the initial volume, this one. Okay, so this value comes out to be what? This is equal to 250 minus 100 by 0.067 into V minus 0.1. This also satisfies the equation. Let me write it as implies P is equal to. Okay, so this also satisfies. How? See, when the volume is 0.1 meter cube, this entire fraction becomes 0. So the pressure is 250 kPa. When the volume is 0.167, then this value 0.167 minus 0.1 and this value 0.067, these two values get cancelled. So 250 minus 100 remains, and this is 150 kPa. So this is essentially an equation of the variation of the pressure with the volume. That is a linear variation. Okay, so the work done, integration PdV. So this is what integration from V1 to V2. This is 250 minus 100 by 0.067 V minus 0.1. Okay, so this, if we do the integration, V2 is what? V2 is 0.167 and V1 is 0.1. So V2 is, I can directly write this, and this value comes out 100 by 0.067 multiplied by, this will be V squared by 2. So this will be 0.167 whole square minus 0.1 whole square by 2, and 0.1. So 0.1 multiplied by 1 integration, it will come out to be V. So there is dV. So this will come out to be as 0.167 minus 0.1. Okay, So if we go ahead, this one will come out 16.75 minus 100 by 0.067 multiplied by this value comes out to be 0.00224. This total comes out to be 13.40 kilojoule. Okay. Now, if we write the steady state energy equation with these considerations, what we'll find? Now, energy equation, if we write, then M2U2 minus M1U1 is equal to Mi Hi plus Vi square by 2 plus Gzi plus Q minus W minus Me He plus Ve square by 2 plus Gze. Now Me is 0, Mi is 0, and M2 is equal to M1. So MU2 minus U1 is equal to Q minus W. Or we can write Q is equal to W plus M of U2 minus U1. So considering helium to be an ideal gas, we can write MCV T2 minus T1. But we have already seen that the initial and final temperatures are same and it remains at 300 Kelvin. So T1 is equal to T2 is equal to 300 Kelvin. So this value becomes 0. So this is essentially just W and this is equal to 13.4 kilojoule. Therefore, the heat transfer to the tank is this value is 0. Heat transfer to tank 13.4 kilojoule. Okay. So is it clear to everybody?
Yes, sir.
Okay.
In the problems of the thermodynamics, the consideration of the control volume, yeah, system, that is a main, that is
Yeah,
a
that is a very critical part actually.
yeah, yeah, sir.
Okay.
I was I was any too much any doubt in this any problem. Now it is any clear.
Okay. Thank you. So let us move on to the next problem then. Okay. So this is a mass loaded piston cylinder assembly containing air at 300 kPa 17 degrees Celsius with a volume of this one. So what are the initial conditions? Initial conditions of the piston cylinder assembly are P1 equals to 300 kPa, V1 equals to 0.25 meter cube, and T1 is equal to 17 degrees Celsius. That is what? 290 Kelvin. Therefore, what is the mass initially? P1 V1 by RT1. Just put in the values. So this is the initially this piston cylinder assembly. It contains air at 300 kilopascal at 0.25 meter cube and temperature this 290 Kelvin. And after that, from an airline at 500 kilopascal and 600 Kelvin, the air is transferred. I mean, air is allowed to flow into the piston cylinder assembly, so that the piston moves up and it reaches the stops. Okay, at the stops, the volume is 1 meter cube. Okay, and the final pressure inside reaches 400 kilopascal and final temperature reaches 350 Kelvin. We have to find what is the mass of air that has entered the cylinder from this air supply line. So this is the mass initially inside the cylinder. Okay, so this is 300 into 0.25 by 0.287 for air and 290. So this value comes out to be equal to 0.9011 kg. Again, finally, okay, this is the final pressure is what? 400 kPa. Final temperature is 350 Kelvin, and the final volume is 1 meter cube. Therefore, what is the final mass of air inside the cylinder? P2 V2 by RT2, that is 400 into 1 by 0.287 into 350. So this value comes out to be 3.982 kg. So initially there was this mass and finally there was this mass. So what mass has entered? It will be the difference between these two masses. Therefore the mass entering the piston cylinder assembly, piston cylinder assembly, that is Mi, is equal to M1 minus M2, and this is 3.081 kg. Okay, the answer. And now let us move on to the next part of the problem. So in the previous problem we have to find what is the total work done and the heat transfer during the process. Now see, when initially this was the state of the piston, now air is moving in. So as air is moving in from this, the piston will move up, and this will essentially be a constant pressure process. That is, it will expand at 300 kilopascal till the volume till this piston reaches a stop and the volume increases from 0.25 to 1 meter cube. Okay, after that, when the piston has already reached the stop, the volume cannot increase any further. Okay, so the volume will be maintained at constant and the pressure will now increase from 300 kilopascal to 400 kilopascal. Okay, so in the second part, that is when the volume is constant, no work is done, right? Since the volume is constant. So the work will be done only in the first part of the process, that is when the pressure is constant and the piston is moving upward and the volume increases from 0.25 to 1 meter cube. So the work is done only in the first part of this process. Okay, therefore the work done will be this constant pressure and the change in the volume. So the constant pressure is 300 kilopascal, the change in volume is 1 minus 0.25, so it is comes out to be 225 kilojoule. Now what is the heat transferred? If we write the energy equation, m2 u2 minus m1 u1, that is equal to mi hi plus vi square by 2 plus gzi plus q minus w minus me he plus ve square by 2 plus gze. So here, see, no mass is exiting the system. No mass is exiting the system. So me is equal to 0. Also, therefore this mass that is entering, we have already found out this mass entering mi, that will be equal to m1 minus m2. And if we neglect the changes in the kinetic energy and potential energy, therefore the heat transfer, is there any doubt? Any doubt?
No, sir.
Okay, 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 okay. So this q will be equal to w plus m2 u2 minus m1 u1, me is 0, so this when you take it this side, so minus mi hi. So this, what are the values? Is 225 kilojoule plus, considering helium to be an ideal gas, we'll just consider u to be cvt and h to be cpt. So what is the initial mass? Mass m2 is 3.982, 3.982 into 0.717 into the initial the final temperature inside is 350 Kelvin minus 0.901. This is the initial mass into 0.717 multiplied by what is the initial temperature? Initial temperature is 290 Kelvin minus m1 is mi is m2 minus m1. We have found out 3 m1 minus m2, that is 3.081 multiplied by this is cp to 1.004 into the final temperature. The final temperature is not the final temperature, the temperature of the air supply line, that is 600 Kelvin. 600 Kelvin. Okay, so if we put in all these values, it will come out to be minus 819.05 kilojoule. Okay, therefore the heat transfer during the process, for heat transfer during the process is equal to minus 819.05 kilojoule. The answer, this is a heat lost actually. Okay, so is it clear to everybody? Is it clear to everybody?
Yes, sir. Everything is clear today.
Okay, thank you. So I think so we have already reached the end.
Oh,
So if there is no doubt, you can leave.
okay, sir. Thank you very much, sir.
Okay, thank you. Please attend the next session.
Okay,
Yeah, okay,
sir.
thank you.